Welcome to Lecture 4, the Data Pipeline. In Module 3, we wired the agent to its tools. Now we feed it data, and we do it in a way that's fully reproducible from manifests. The promise on this slide is bold: Delta plus Qdrant in 13 seconds. From a clean cluster, a single Spark application writes Delta tables on MinIO, registers them in Unity Catalog open source, and a separate Kubernetes job batches embeddings into Qdrant. End-to-end. No notebooks, no interactive sessions, no tribal knowledge. The win is reproducibility. The CRDs and job manifests live in version control alongside the chart. Anyone on the team runs Helm install plus kubectl apply and gets the exact same lakehouse. Notebooks drift, manifests don't. In the next two slides, you'll see the actual indexing job that pumps documents into Qdrant, and the 3 commands you run to verify the whole stack actually has data in it. The vector index job. Not a Spark job, just a regular Kubernetes job. A small Python script that batches documents through TEI for embeddings, then upserts the resulting vectors into Qdrant. Walk through the code. We open a Qdrant client pointed at the Qdrant service inside the namespace. If the target collection doesn't exist, we create it with the right vector dimension and similarity metric. Cosine. 768 dimensions for BGE large. Then we read the source rows. In our case, product documentation chunks loaded from a Delta table through Delta ARS. For each batch, say 64 docs at a time, we hit TEI's embed endpoint over HTTP. TEI returns a list of float arrays. We package each into a Qdrant point with the original metadata as the payload, and call client.upsert. That's it. The whole indexing flow is maybe 60 lines of Python packaged into a Docker image run as a Kubernetes job. No Spark cluster, no DAG framework, no notebook to babysit. The job manifest is part of the Helm chart, so a fresh deploy of the cluster runs the index job automatically. The key idea: embeddings are just batch HTTP calls. Vectors are just dictionary inserts. The infrastructure for this doesn't need to be heavy. Verification. The whole lakehouse confirmed in 4 commands. Command 1. MCLs against MinIO. MC is the MinIO client. We point it at the namespace's MinIO service and list the bucket. We expect to see Parquet files written by the Spark application. If they're there, the Spark application ran, and Delta wrote successfully. Command 2. A curl against Unity Catalog OSS. The REST endpoint returns a JSON document listing the catalog, the schema, and the table. We confirm the table is registered and points at the right Delta location on MinIO. Command 3. A curl against Qdrant/collections. The response shows our product docs collection exists, with the expected vector count and dimension. If we indexed 2,000 chunks, we should see vectors count 2,000. Command 4. A small Python snippet using Delta ARs. Open the Delta table directly, read its rows back. This proves you can read what Spark wrote, end-to-end, with the exact same library the agent's tools use at runtime. If all 4 come back clean, you have a working lakehouse. Delta tables on object storage, UC catalog populated, vectors indexed, code reads it back, from manifests, in seconds. That's the win. In Module 5, we wrap the course with deployment and evaluation. See you there.